My name is Amrith. I'm one of the founders and the CTO of this company called ParElastic. We make software for databases and very closely related with MySQL. So happy to talk to you guys about scaling your databases using techniques which are common with parallel databases. Just as a quick background to get an idea for where everybody's at. How many of you are familiar with what a parallel database is? Yes, no, show of hands, raise your hand, nod. Okay. How many of you here use MySQL? I assume everybody. Okay. How many of you are familiar with sharding? Okay. How many of you are using MySQL in some cloud, one cloud or the other? Amazon, other clouds? Anyone using any other clouds? No. All right. So I have about 70 slides, but as Tim has told me, it shouldn't take more than about an hour. There's going to be a demo at the end, and if you tweet and include any of these words, you will be part of the demo. So feel free to tweet nice things if you don't mind. And make it interactive and ask all the questions you want. Try my best to answer that. I've also tried not to make this a marketing presentation. So I'm not going to start with slide number 1 and tell you about our product and end with here's how you buy it. I wanted to make it something which would be useful to you, even if you didn't buy it. So with that, let me start with this. Simple picture of an application. There's a database, there's some cache around it, and then you have a whole bunch of clients trying to connect to this application. And my monitor, this. Let's try this again.
There it is. Yep.
Okay. And one of the things which I've always noticed is when people build these applications, they try their best to insulate their database as much as possible from all the clients which might be trying to get at it. Anybody have ideas why this might be the case? Thoughts? Ideas? You got a bunch of clients up there, you know, mobile client, Firefox browser, some kind of tablet. But everybody tries to go and get the responses off the CDN if they can. If they can't, they try to get the response off the cache. They really try to avoid hitting the database. Any ideas why? Well, here's one reason why. If a request could be processed by a CDN, the response time is this little green line at the bottom. This response time is in milliseconds, by the way. If the exact same request had to go to a cache, you notice that with concurrency, your response time goes through the roof. On the other hand, if the same request had to go all the way back to the database, you notice that your database response time just climbs to the point of being totally unacceptable. If you have some kind of ceiling on what you think the responsiveness of your application has to be, if you start hitting the database all the time, you're toast. So people try to reduce how often their database gets hit, but that's not always possible. And the reason why that's not always possible is if you have an application which is interactive, where you expect people to interact with the application and they want to see updated information all the time, you can't push everything into a cache and expect the cache to give you the stuff which is good enough for you. Come on in. So as concurrency increases, you start to notice that your database has this response time climbing off into the roof. And for all of you who are used to financial charts, up and to the right, not a good thing. So there's a couple of ways in which you can try and address these problems. Two common ways are scale up and scale out. If you're all familiar with what scale up and scale out are, we can skip the nice picture. You wanted to see the picture. So It's there. Everybody familiar with these concepts? Not familiar with these concepts? Okay. Scale up when you get a bigger and bigger server. Scale up when you get a lot of servers of some size. And you make them all work together to do the same thing. Both of them move large amounts of stuff. It's just a question of how you want to solve this problem. There are some inherent problems with scale up. You get one thing, it's ridiculously expensive. I didn't have a nice picture of a dump truck tipped over, but you know what happens when one of those things go over? Scale out has other problems. Moving Earth is a problem which you can scale horizontally. Databases are not necessarily as easy. So the rest of this talk is going to talk about how you scale a database horizontally. So why is scale up not a good approach? So this is some, how are you? This is a set of results from a survey, from a study which was published by some guys at the State University of New York. For all of you Amazon types, those are EC2 instance types, or RDS instance types. The benchmark they use, standard TPCC. And they measured what they could get for TPMC. That's the number of transactions per minute of this particular benchmark. Okay, you can get a bigger server, but there's some ceiling on the throughput you can get. And in this case, you'll notice that if you get a 4 extra large, it's actually not as good as a 2 extra large. Okay, I get 6,000 transactions, that's great. Well, here's the unfortunate truth. The exact same data, I just added what the cost is. So the line here says, what does it cost me to get one additional TPMC? With a small, it's $2.36. With a large, it's $15.34. In other words, you can get a bigger server, but it's not cost effective for you to get a large server. You really want to get the most optimal size server, distribute your workload across it, rather than keep going for the biggest server. So if you want to get one additional transaction, that's going to be the marginal cost on a 4x large. If you want to get one additional transaction, even though you're limited 1,800, that's the cost. So the takeaway from this is scale up is not inherently the best solution. Not only the fact that there is a notion of a largest server, there's also a notion of the largest data volume you can attach to that server. So if you happen to be running an Amazon cloud, there's a cap on the maximum data space you can have. So what parallel databases do is try to address this problem in one of several different ways. And I just want to point out, parallel databases are not new. They've been around for a very, very long time. The column on the left shows some research stuff. For those of you who are interested, you search for those names, you'll find the appropriate papers. And the column on the right is companies which have actually produced products using these kinds of technologies. So 1984 is the first one that I've been able to find, that's Teradata. And more recently, you've got a whole lot. Right around here, I know of at least 3 companies which have done something like this. I also included MapReduce because, in large part, MapReduce is a parallel database technique. It's not a relational technique, but it's a parallel technique. So this is not something brand new that you should be scared about. So some of you said you knew what a parallel database is, but not everybody did. So let's talk about what they are very quickly. Any system which tries to improve performance by trying and doing things in parallel. Every operation of a database, try to do that operation in parallel rather than on a single machine. Everything down to index creation, everything down to a scan, everything down to sort. Try and do it in parallel. That's what a parallel database is. And there are commonly 3 different architectures you can have for a distributed system. They can be either shared memory, shared disk, or shared nothing. I hope these terms are things everybody's familiar with. Yes, no? Okay, I see a couple of nods, so I'll take it as a yes. But shared nothing is typically an architecture where you have multiple machines, and each machine has some private resources, memory, disk, CPU, and it performs operations based on the information on those private machines. So you have a distributed shared nothing database. That's typically what you call a parallel database. So most often you see these in analytics. Netezza, Vertica, data warehousing companies. But more recently, you found Oracle Exadata going into the transactional space. So parallel databases are available in the transactional space. Exadata base price about $3.5 million last I checked. I don't have that kind of money hanging around, so let's try and see how we can do this a little cheap. Any questions so far? Okay. So what's a shared nothing parallel database look like? Right up top, you've got your application. Your application is going to talk to this big box here, which is the parallel database. It talks using some standard encapsulation, some standard language. The encapsulation could be JDBC or ODBC. The language could be SQL or some extension thereof. If it's MySQL, the encapsulation is libmy very often. Language is still SQL. And the components of a typical parallel database are a partial planner. I receive a query. I want to take it apart, figure out what it is you want to do. Your actual data sitting on a bunch of machines. And the real guts of a parallel database is this thing called query orchestration, which is, for the most part, what the rest of this presentation is all about. Is how do you take a query from an application up here and execute it on a group of data which is sitting on this collection of machines down here and produce a result set which makes it appear to the application like you're talking to a single instance of a database. That's basically what this query orchestration business is all about. In order to do that, there's other things which a database needs to have. Databases need to be ACID. You need the notion of saying that I made an update to a record, that update is durable. I have a notion of a transaction, such that my changes need to either be all in or not in, and if you're making changes to the same thing, there's some standard way in which we resolve these conflicts. That's transaction management up there. And of course, when you have a bunch of machines, you need to have some way of managing all of these, please.
How much each slice should know about other slices?
The goal of a parallel database is each slice is entirely and totally oblivious of the other slice. In practice, that's the ideal of a shared nothing system. Each node in a shared nothing system is entirely and totally oblivious to every other node. Now that's theory. In practice, these slices need to talk amongst each other. At the very least, they need to know, how do I talk to the other node? The moment you say I need to know how to talk to another node, it means you know that another node exists. What's the IP address of the other node? Oh, is that IP address for the node or some pseudo IP address for that and its failover pair? You start pulling at that, and eventually you'll notice that each of these has some knowledge of the others, but as little as possible. The approach which I'm suggesting here, every node is entirely oblivious of the other. Okay. So let's talk about a practical scenario. And for the purpose of this scenario, I just have a simple example. There's 3 tables involved. And I also have 3 slices. So these are 3 machines, each running MySQL. And no machine knows of the existence of the other machine. Right? And something up above these machines created this schema. So the first row on top, CID, which is customer ID, and name, the name of a customer. The second, an order ID, a customer ID, and an item ID. And the bottom, a bunch of items. So the simplest case, all tables exist on all nodes. Okay? So there's a bunch of customers. On the first node, I happen to have customers 1, 4, 7, and 10. And the code for all of these slides is a column in red is a discriminator column which the system uses to decide where to store a row. Now, you realize there's 3 nodes, and the node with 4 could have been stored anywhere. but the system has some method to where it stores data, and it uses the discriminator column, in this case customer ID. And similarly, I have 12 customers, 1 through 12 for the customer IDs, and it so happens that I use customer ID mod 3 to decide where to store it. That's entirely left up to the implementation. It just was easy to make those slides that way. The basic idea is, given a customer ID, I know where that customer ID goes. Okay? Let's talk about items. Go ahead.
Gus, do you have any suggestions for techniques so that if you need to add more machines in there, you don't have to completely remap all the data?
I have a 70-page patent which tells you exactly how to do that. Happy to chat with you about it. But I was at Netezza, which made machines which look like refrigerators with hundreds of nodes. And someday I had a 200-node system. He said, I love this stuff. I want to upgrade it from 8200 to an 8400. And we said, oh, we'll send you an 8400 and an SC will migrate the data for you, send the 8200 back. Adding a bunch of nodes was not easy for exactly the reason you said. Long ago, the Egyptians figured out that moving blocks of stone is really, really possible. It's no different with blocks of data. Resharding sucks. So there's no two ways around it, but we'll talk a little bit about how you get around it. Okay? So items table, again, I distributed the items table on the item ID. So I got 8 items, no, 6 items. Typical things you'd expect to find in a kitchen. And I distributed the customer table, I distributed the order table based on customer ID. Okay. Now this order table has items as well. It has customers. But since I'm distributing by customers and there's method to this distribution, if customer 1 places an order, his order is going to show up here. Some mechanism takes care of that. Now the question is, this guy ordered this 102 thing. He ordered a bowl. The bowl, unfortunately, sits on another node. While this cup is local, bowls are remote. In a typical sharded environment, this is we don't like this problem. Because in order to answer most reasonable queries, you're going to have to join these 2 tables. The objective of a parallel database is the application should be entirely oblivious to the location of the data. And if you're building a system like this where you want horizontal scale, you need to figure out how to address these kinds of joins. So I'll fill in the rest of the stuff here and give you a couple of examples of all the people who ordered bowls were. Well, they happen to be all over the place. There's nothing which says one customer can or cannot order a bowl. This particular picture, keep it in mind, because we're going to talk about the exact same illustration carrying forward. There's things to keep in mind. The customers table is distributed on customers. The orders table is distributed along with the customer table on customer ID. And the item table is distributed on items. In other words, you can join these 2 anytime you want. You want to join these 2, you've got to do a little bit more. Okay? All right. So my question is, who bought bowls? So if I didn't tell you that these things were on different machines and all that, and I executed this little query at the bottom, what you were basically going to do was you're going to say, item name is bowl, scan this table, get me the item ID. Okay, now get me all the 102s in the item ID column. Use that to find me all the names. So literally, your database is traversing all of these paths. Except some of the paths go across nodes. This path is a relatively easy path to go. These paths are hard. And the objective of a parallel database is, if you issue this query, the results you're going to get are Abel, Grace, Henry, Fred, because they're the people who ordered bowls, no matter where the data exists. And to your point, if you added 4 more nodes later, it should continue to work without your having to change a single line of SQL. That's the objective. Okay. So what's the benefit of doing all of this stuff in parallel? We talked about a parallel database. Okay, so I got 3 machines. Each one has its own disk, has its own little copy of data. If I were to scan the order table now, I have 3 machines scanning it in parallel. So, a quick example of what that means in practice. I populated a table which happened to have 2 billion rows of data. This happened to be running on an M1.4.4 XL on Amazon, which today's price is $1.80 an hour. I took the exact same 2 billion rows of data with ParElastic, small piece of marketing here, put it on 5 MySQL slices. Did the exact same query. I did it on a cold system, no caches, nothing. The scan rate to the disk is the same, but each server is scanning 1/5 of the data. You get your results in 1/5 of the time. Very simple math. If you have queries which are going to be disk bound, a parallel database will kick an SMP database any day of the week. Okay. And oh, by the way, it doesn't hurt that it's a little bit cheaper. Okay. Questions so far? All right. So how does a parallel database actually do all this stuff? Select comp star from customers. That was the query. 2 billion customers worth, select comp star. Okay. The customers table is distributed by customer ID. Oh, how many of you are familiar with this bubble representation? Reasonably common way of representing a query parse tree. But select comp star from customers. That's the query which was received in SQL. You're going to scan the customers table. The 2 lines of the circle indicates that it's going to be executed in parallel. Each node is going to perform an aggregation operation, and each node is going to say, I got 2 billion over 5 approximately. And then all of them are going to ship that 2 billion over 5 to some central place, which is just going to count them all up. I got 2 billion rows, each one's got 1/5 of that. They come up with the answer of about 1/5 of that. You send that answer somewhere, it adds them all up and says, yeah, you got 2 billion rows. And that's what you return.
So in my ISAM, it knew the count for every index, but InnoDB doesn't.
InnoDB actually would also do it. This is just an illustration of what a database would do. I could have used a slightly more complicated query, but I thought this was a good place to get started. InnoDB has an approximate count. If you shut down the database and you restart it, it doesn't always rely on the count. It will sometimes attempt to do the full count. This was an actual InnoDB table. And sometimes it takes 16 minutes. Okay. All right. So let's talk about what a parallel database does, and this is the way in which we do stuff at ParElastic. You got a bunch of servers. They all run MySQL. They run MySQL means they can run Percona, they can run MariaDB, they can run any variant of MySQL they're on. Your application talks only to us. You never talk directly to the database. You open a connection to ParElastic. You open that connection exactly the same way as you would if you were talking to a standard MySQL server. You have a JDBC URL which says JDBC:MySQL IP address, port number, exactly the same thing. The interface, unmodified. No change to your application. It's our job to make this collection of databases play well together. For the rest of this presentation, I'm going to represent a collection of databases at the bottom. I'm going to assume that each one is, I'm not going to talk about things like mirroring and how many of them are copies of each other. Each one is a slice of data, 1 over n of the total data in the system. Something like that. So here's a simple query. The one we talked about. Give me the names of all the people who ordered bowls. In order to find the people who ordered bowls, you start with a bowl. You have to go from the item table to the order table, find the order IDs. From the order table, go to the customer table. So if you did the same kind of bubble picture, this is what it would look like. So you have items and orders being joined on the item ID. The result is a bunch of customers, which is joined with the customer table, and that produces your customer names. Everybody okay with the equivalence between these two things? Okay. So let's start. Every arrow in a bubble diagram, and there's a bunch of arrows here. We're going to talk about each and one of these arrows. Each arrow has a geometry, which is what's the column being sent, what's the collection of columns, but also it has a distribution. So you're scanning the table item. The distribution of that stream is however the item table happened to be distributed. How is the item table distributed? Anybody? Anybody?
Uniformly over the,
Using which key?
item
Item ID. So this one's distributed on item ID. Okay. This one's distributed on, well,
Customer ID.
customer ID, exactly. It would have been just as bad if it was order ID. It's not the same. That's the important part. So I want to join these two. What's the problem here? An item need not always be on the node where the order is. You can't just execute this join. You'll get partial results. So at the very least, that join needs to be, you need to do something in order to make that join work. And in a parallel database, you either broadcast or you redistribute. In this case, I say broadcast. But for the purposes of this query, we will find all of the items with the name bold, and we will send those to a place where you can execute the join. Then you execute the join, and then you come up with this one. Okay, since we've done a redistribution here, what's this one distributed on for that join?
depends on where you send it.
Exactly. I sent it to the order statement, so both of these are now going to be distributed on customer ID. Okay, so that join's happening. And then you produce your results there. So at some level, all a parallel database is a bunch of databases, but this algorithm which says, that's the query, how is the data distributed, how do I make this graph something which can be executed in parallel? That, in a nutshell, is what a parallel database does for you. Okay, so let's talk about what the final result is. This is what the final result would look like. So you can collapse this basically by saying, you want to do this all in parallel, so I'm going to collapse it by saying, this is a redistribution followed by a three-way join, and you're all done. The transformation from here to here is all our software does. We're a SQL to SQL translator. This is a redistribution operator. This is a join. There's a sequence of steps which you have to execute. You execute them, you get the customer names. You do it wrong, you get the wrong names. That's about it. That's our query class. I give you this query. I say broadcast to T1, select my ID from items, and I use T1 in this join. What our software does is it parses this, looks at the distribution of each of these tables, and produces this, and then says, MySQL, go execute. That's it. Now, this is all stuff that you can do in your own app. It's really painful to do it in your app, but if you wanted to, you could. I did ask up front how many of you knew what sharding was, and a lot of you probably look at this and say, this looks a whole lot like sharding. So the obligatory, this is not sharding. From my point of view, I think sharding is an application architecture. Parallel databases are database architecture. And you need to make absolutely no rewrites to your application. We have a bunch of examples of that. But by virtue of the fact that sharding is an application architecture, it means that you're building something into your application which needs to know where the data is. Your application is data location aware. I'll send you the slides, don't worry. And most importantly, you do not want to be constrained. Your application should not be constrained in what queries it can ask any query. It's up to the database to get you the answer to that query. That's basically what a database is. MySQL doesn't say, oh, well, you asked me that query, sorry, I can't answer. Answer whatever query the app needs to. So the application developer focuses on the application, doesn't get bogged down in, where's this data? Is it distributed this way or that way? And I redistribute it, and what happens to my queries? All of those kinds of things. It happens sometimes. Not all schemas are shardable, or at least not all schemas are easily shardable. You may have to denormalize your schemas. Not always a good thing to have to do. Something to keep in mind. All right, so what does it look like with us? You've got an application that talks absolutely standard interface, whatever it was. If it was a application built on libny, we would use libny. If it was ODBC or JDBC, same story. And it talks to us exactly the same way. For a whole bunch of applications we work with, we go find a config file somewhere where there's a JDBC URL for the database, we point it to us, and we're all done. Behind the scenes, we distribute the data, and this answers part of your question. We distribute the data over some collection of MySQL servers. We do it in some deterministic manner based on a column, a bunch of columns.
You would not consider generating say an index as another column, which is where you put it, so that you can be sharding more easily.
I personally think resharding is a bad idea. So the reason why you want to shard or you want to distribute based on columns in the schema is because people write their queries based on columns in their schema. And you want your data located based on the queries which are executed. I can create another column, make it an auto increment, and distribute based on that, and that is guaranteed to have a really high cardinality. But it means virtually every join, you're going to look and say, I have no idea where the rows for this join are coming from. And you'll end up doing a whole bunch of data shuffling. So if I have the example of customers and orders, and I know that somebody is going to join the customer table and the order table based on customer ID, I'll distribute them with customer ID. That way I'm guaranteed locality where I'm in.
But then you have to deal with the issue of, say you've got 100 MySQL databases.
Mm-hmm.
Business goes way up, you go to 200 MySQL
Exactly.
databases.
Great, straight man. You should watch the next slide which comes up. So we just make multiple database servers act together as one, and as your servers fill up, spin up a bunch of them. Part of our IP is the ability to use those servers without you having to move anything. We'll guarantee co-location and you don't move anything. That's basically that's part of what we do in deciding where to store it. Yeah, we can talk at length about how we do it. I think it's a pretty cool piece of code, but it'll probably take more than an hour to do that. So at the core, we distribute your data as an application over some collection of databases. Okay. There comes a time when you want to join two rows which are not on the same database. Well, remember I told you we had to move rows from one place to another in the middle of a query? We have a whole bunch of nodes, also running MySQL, with no persistent data. And we use them solely for the purposes of intermediate computation. When you look at a MySQL query plan, you notice that they generate temp tables as part of a query plan. Think of this as the place where we store our temp tables.
Where is the database? Is that your database or VS?
It's just a standard MySQL database.
No, and the storage, where is it stored? In the cloud or?
It's stored, so typically if you are building an application, you want your data to be where your application is. So if you're building your application in Amazon's cloud, all of these are going to be probably in Amazon as well.
Okay, so you don't store the data. The person provides you with a link to the data.
Mm-hmm.
Okay.
That's right. So it's just, you're going to store the data in some MySQL database in wherever your application happens to.
Okay.
So if you're running it in Amazon's cloud, it'll be in Amazon's, either in EC2 with MySQL or RDS. If you're running it in Joins Cloud, something like that. If you're running it in your own data center, these are MySQL instances in your own data center.
Okay.
Okay? As you're running queries, if you find that you need a lot of intermediate compute power, spin up a bunch more of these. There's no persistent data, you don't have to replicate a whole bunch of stuff. Spin up, use them for something close to 55 minutes, and then shut them down, because you paid for an hour anyway in Amazon. So you don't need to hang on to those forever. Okay. So how do we distribute data? You had a question about how we distribute it. These are the ways we support for distribution. You can distribute it. You distribute tables based on whatever their role is in the schema. What are the queries you're going to run against them? You can either distribute a table randomly. For example, log files. I'm never going to join anything with them. I'm only going to do scans and filters against them. Distribute it randomly. I don't care where the row goes. Other tables, which are going to be used a lot for joins, distribute them deterministically based on some column. And oh, by the way, I have a whole bunch of other tables which are reference tables in my schema, like in a star schema. These are your dimension tables. You define something called broadcast. The table is maintained transactionally consistent across all dimensions. So whatever query you come up with, or whatever schema you come up with, you make a one-time choice of how you want those tables to be distributed. After that, it's up to the database to figure out how to actually execute your query. Are the tables co-distributed for joins and all of that stuff? That's all magic for you. We talk about multi-tenancy later. It's just a placeholder to say there's other distribution types if you do use multi-tenancy with us. So here's some screenshot versions.
So when you say co-location, how do you indicate, or do you even indicate how to co-locate identifier IDs?
Yeah, so we have a couple of ways you can do that. The simplest way is you annotate your schema. Create table customer, distribute on customer ID. There are other ways in which you can do it where, so that basically means you have to change your install program or something like that. We have other ways in which you can do it without changing your install program by giving us hints. Where you give us a hint which says, oh, if you see a table like this, here's how I want you to install. So suppose you don't want to change your application installer one bit. You give us hints on the side, and we'll make sure the distribution is appropriate. Basically what you're telling us is, what is that discriminator column or group of columns? So here's a simple query. Against the customer table was distributed based on customer ID. I have no idea where customers with a name like Bell happen to live. So send the query down. The database determines that I have no idea where these rows are. It sends it to every place where it can possibly be. And some group of them are going to return results. We just send the results right back to you. Where is SQL to SQL rewrite? That's it. Sounds good? Seems pretty straightforward. It's not hard. Okay, so let's start from orders where customer ID is 7. Okay, this is getting a little bit more interesting. How is the orders table distributed?
By customer.
By customer. Okay, so if customer ID happens to be 7, you can tell a priori where that may live. So we get a little smarter and we say, if customer ID 7 happens to exist, it's going to be there. Send it there and only there. This is one of the reasons why you definitely want to distribute based on the primary key. Oh, there's one of the good uses for distributing on your primary key. I can narrow it down to exactly one place. Still, this is not hard. All we're doing is we're figuring out which one place to send it to and send it. That's about it. Okay. But in this case, your application has absolutely no idea how many nodes there are under the covers. Did I grow them? Did I shrink them? All of that stuff is totally transparent to you. Add a couple more nodes, your application doesn't change one bit. Okay, let's keep going. Give me the name of the customer and all of his order IDs. If you wanted the order ID and the customer ID, that would be easy. I could get it from the order table, but I want the guy's name. Okay, so I got to join the orders table and the customers table. Customer was distributed on customer ID. How was orders distributed? Also customer ID. So this is a co-located join. Since we have no restrictions on which customers they are, we get all the nodes to execute the join. And each one produces only its fraction of the results there. We just send the whole thing back. Again, we're just in the middle, translating SQL to a different set of SQL, getting you the results, and we're done. Okay. This all seems really simple. Okay, here's where it gets a little bit.
Yeah, that's a simple case right there. How's failure dealt with?
How's failure dealt with? Okay, so halfway through the query, that one queues. I have no idea how many rows these return. Your application gets an error.
Okay.
And a partial result. Restart is not a trivial thing to do. In the case of a simple query with a join and an implicit transaction where there's nothing else going on, yeah, you can kind of sort of figure it out. But if you think about it, all I'm pushing down to MySQL here is the exact query which I received. there's no ordering on the results. So even if I kept a little counter which said I've gone through 652 rows, if I rerun the query, there's absolutely no guarantee I'll get the same result. It so happens that most of the time we will, but there's no guarantee.
But in the same way, your client application still thinks it's only talking to one MySQL server.
Still thinks it's only talking to one MySQL server. It doesn't know that, oh, the third one failed and I got to retry the third one. None of that happy stuff. You got a partial result set, you got an error.
Okay.
And then you retry the query, and behind the scenes there's an HA failover, which happens that node is anyway replicated to someone else, your query will go through the second time.
Okay.
To decode the partial result and the error, do you need to rewrite your application to anticipate that?
It's the same thing you would get with MySQL. If you're halfway through a query with MySQL and you get an error, you're halfway through. So you're buffering results from MySQL. So I execute a
Or
query.
you're running on a cursor?
Well, even if you're not on a cursor and you're retrieving data a block at a time, you've retrieved 17 blocks of data, there's a disk error on one of them. The query is still executing while you're retrieving data. There's a disk error and the thing can't read anymore, and he goes, you're going to get that halfway through your results. Typically, in an OLTP style application, you assume your result sets are going to be small. You don't see this too often. If you run a report which is going to produce thousands of rows of data, yeah, if you're unlucky, halfway through a result set, you get an error. Then you got a partial result that is, you get to restart. Okay. So here's where things start to get a little bit more hairy. Same query as last time, except I want you to give me the results in order. Okay. Each one of these can give you their portion of the results in order. Somebody's got to put all those pieces together and get them all in order in one place. Here's how we deal with that. Again, we want to stick to being in the business of rewriting SQL. We don't want to be in the business of executing SQL. That's a whole different problem set to deal with. So at this point, I have 5 MySQL servers which are all going to execute a join and produce an ordered result set. What do I do with that result set? I drop it onto a temp node. That's MySQL too. He's going to produce the ordered result set for you. Now, there are other ways in which you can solve this problem. There's the sharding approach, which says we're going to do the sorting in some central location. If that location is not MySQL, it's left as an exercise to the reader whether it got collation exactly right the same way MySQL did. And God forbid your collation in some funny language is not exactly the same as MySQL, you get a bad result. It's MySQL, it knows how it collates, let it do its job. We'll stick to SQL rewriting. Okay? So here's an example where we start using these processing nodes. Go ahead.
So the off-the-shelf MySQL database manager dynamic, are they created just in time as needed, or do you have a...
You have a collection of databases which you spin up and keep ready. There's a little daemon sitting there running and saying, how busy are these servers? And if I notice they're getting very busy, I go and produce a couple more. There's no persistent data on there. I can just spin up a M1 large instance and with a specified AMI, just add it to the fold and say, one more worker available if you so desire. And periodically you read the list of your temp servers and you say, hey, system workload just came down. I don't need 5 anymore. I want to get rid of a couple. Within the bounds of some policy, if I determine I want to get rid of one, then you pick the one which probably is closest to a billing boundary and then you pick that. So, all right, so that's where you use a temp node. Okay. I'm not going to ask everybody.
Do you really need that node in order to sort your result? Because you already have all nodes, with a kind of result available.
Mm-hmm.
So do you create a special node because it's easy for you?
The reason I created a special node is because, so if you're talking about a data set where everything is in, ASCII, simple ASCII, collation is very straightforward, It's fine. What if you get into some situation where collation is not straightforward? If you're not going to get MySQL to do your collation, you have to guarantee that you got your collation absolutely correct. Because you're getting 5 streams off of here, all right? All 5 streams are sorted. The one place which you want to do this not MySQL-based sort is a merge. You've got 5 streams coming in. You look at the first row on each one and say, which one's the lowest? Send that one out. Which one's the lowest? Send that one out, and so on. That's a merge sort. If you, for some reason, in your determination of which one of the 5 is lowest, don't follow the exact same collation semantics which this guy followed down here, bad things happen. Why do we want to get into the business of being SQL executors? So from my perspective, call this religious, we will execute 0 SQL. MySQL does a perfectly good job executing SQL. Let it do its job. Your results are guaranteed for you by MySQL. I can make that play.
Would you allow one of your storage nodes to play the role of the processing node?
These are just pictures for the purpose of illustration. All this stuff gets doubled up. Very, very heavy. Yeah.
In what price? What performance price?
We'll just charge you for it. We'll just charge you for it. No, I'll show you the price. The performance price is not all that bad.
With the use of this, how do you call it, the processing node?
Sure.
Or without?
With
I'm saying that even without it, there is some price probably. But with it, the additional price.
We'll see the performance. There's a whole bunch of performance numbers as well. Okay, slightly harder query. And a simple sort, yeah, we've had this argument a lot of times. Here's when it becomes interesting. The important part about a parallel database is you want to do as many things as you can in parallel. Okay. Give me the name of any person who has the letter E in their name and the count of the number of orders they had. That's what that funny piece of SQL up there has. Okay. So it's a join between the same 3 tables. There's going to be some redistribution going on along the way. Okay, standard SQL. We rewrite the SQL and execute it as follows. First, we do a set of operations on these nodes. But then we send intermediate results, not to one, but to a whole bunch of these. And again, driven by policy, we make a determination on how many of these you want. This is a grouping aggregation based on item name. In the example I gave you, there were a total of 6 items. I can do that on my hand. What if you had 6 million? If you had 6 million buckets and you had one place where you wanted to put them, this is one of those places where MySQL gets into trouble. Scanning MySQL is brilliant. Start doing grouping aggregations in MySQL, your performance starts to go off the end. Okay. What if we were to distribute the intermediate results by the column you're grouping on? If there were, in fact, 6 million things you were grouping on, each one gets only 1.2 million. That's where parallelism starts to come in. As long as you can do your operations in parallel, you're benefiting from it. If you saturate on one node, you're not. So we'll talk about the performance of that, to your point, Doron, in a second. But these are the kinds of things where you really don't want to implement this in a single point. You want this to happen in parallel. And again, whatever results happen to come out from that, ship it straight back to the user. We're all done. Okay? You talked about the overhead. So just for the purpose of measuring the overhead, we did this benchmark. Also done in Amazon. Network round trip time was 0.35 milliseconds. A single MySQL deed, this was a M1.4XL, can't get any bigger. Over a long period of time, query response time was 15 milliseconds, 15.7 milliseconds. And I managed to contrive in such a way that for the purposes of this benchmark, a single MySQL server was going to get the brunt of the attack. Some queries to this one, some to the other one. The query response time was 17.03. The net overhead we added, a little over a millisecond. Looks bad here. Wait a bit, you'll see some more performance curves where you'll think 1.3 milliseconds is nothing. hold that value. The overhead is not a whole lot more than a couple of network round trips. So by adding us in the data path, you're not paying such a huge penalty. Okay. How's this? Line on top, MySQL performance. The numbers are the number of milliseconds for a transaction. Green line at the bottom, ParElastic happen to be running on the same 5 nodes. Small concurrency, yeah, doesn't seem that big. This is about a second, it's 300 milliseconds. Well, what happens if this is a web app and you have a timeout at something like 1.5 seconds? You just went over the cliff there. If there's a person sitting at the end of the wire, he's pressing refresh. Just made this problem a whole lot worse. So your 1 millisecond overhead is peanuts in comparison to your transaction time. And this is with 5 nodes. If you have even more load, make it 10 nodes. Your application doesn't need to know the difference. And this is not specific to us. This is something which goes all the way back to the papers which I talked about earlier. Parallel databases, the performance just from this is dramatic. So, this address your question, Goran, about the overhead? These are standard transactions, standard benchmarks.
What about if using the processing disk, so the processing MySQL? This
is with processing nodes, yes.
This is with processing nodes?
Absolutely. I don't get to control what the queries are. It's a full-blown transaction. It starts with begin transaction and has a whole bunch of selects, joins, group buys, updates, inserts, deletes, commits. There's a whole bunch of redistribution going on, a whole bunch of processing node users. So, okay. One of the important things about building your application in the cloud these days is this whole notion of multi-tenancy. You build an application, happens to be, a website, it happens to be something which is driven by a database, and then you decide you're going to sell it to thousands of people. Just from the perspective of simplicity of building your application, each person using this application has their own portal into the application, and for simplicity, you say they have their own database. Now, before long, you get successful, and you get tens of thousands of databases. That's this column here called simple MT. I give each customer their own database. So we've got 20 people in the room, we got 20 databases. Each schema's got 70 tables in it. You just got 20 times 70, 1,400 tables. This gets out of control pretty fast, but it's really, really easy. You have your database, the application just switches each query based on your login credentials to whichever database you want to go to. It also has some unfortunate problems because MySQL's response time is not very, very good if you have a large number of databases. As you have more and more databases, MySQL tends to choke pretty good. The other thing is, if you have a lot of databases, let's assume you have 10,000 databases. You can't have 10,000 databases on a single server. So you pick some magic number. Your DevOps team picks a number and they say 500. 500 databases on one server. Okay, now you got 200 servers. On some one server where I happen to be, Michael happens to have a database as well. And being the bad SQL programmer I am, or since I happen to have a very, very good day on my site, I get a lot of traffic. His site just got a denial of service attack. That's the bad neighbor effect. By virtue of the fact that you've got a fixed size container and you put some number of databases on each one, you've got a bunch of challenges. So there's several ways to solve this problem. One of them is to build multi-tenancy into your application, where you commingle data yourself, you consolidate a bunch of tenants, you put them in one database, everything sits in one monstrous big database. And your application determines Tim's issued a query, so I'm going to do this other little magical extra where clause, so Tim gets only his answer. Michael has his query, he gets only his answer. Your code node just had to determine which client, it needed all this additional stuff based on where data is stored. Again, as far as your application goes, it should be simple. It should just query the database and get the data it wants, not have to bother, oh, is my data on this database, that database, is it mixed with somebody else's data? While you improve the utilization, you have problems as well. Okay. Not the end of the world, right? So think of a typical application scenario. You have a bunch of app servers, you have a bunch of database servers. You did this application multi-tenancy, and you need to roll out an upgrade which, in the app servers, which causes a schema change. Try doing a rolling upgrade. Can't do that. Your underlying database is all locked to one schema. You have one user who decides they want to change and they want to customize their application in some way. Oh, by the way, that requires my schema change. Can't do that either. So in reality, you have a database which is constraining the way your application has to work. Our view of multi-tenancy is that you're talking to ParElastic, we virtualize your database. We commingle the data somehow. We reduce the number of databases. But we do it in such a way that if one database wants to modify its schema, fine, happens totally transparently. You don't need to know about it in your application. You can customize it, you can do rolling upgrades, you can do all of that. I'll give you a simple use case. Happens to say Acquia up here, so Andrew. Andrew is one of our dear friends from Acquia, so we'll let him talk about Acquia.
So I'm Andrew Kinney. I run cloud engineering at Acquia. Acquia, for those of you who don't know it, is the large enterprise Drupal company. So our mission is helping spread Drupal's adoption globally. Everyone these days, from Al Jazeera to CNN to the White House, is running Drupal. Even the White House goes back to Drupal. So we have 4,000 plus servers in Amazon's cloud, and let's just say 1,000 plus of these run MySQL. If there's a MySQL problem out there or a challenge, we're probably facing it. We have a Drupal SaaS product. We have a Drupal PaaS product. We have sites that are doing tens of millions of page views in a given day. We're doing billions of page views in a given month. So we are looking at a number of different ways to optimize our MySQL problems. One of these is with Drupal Gardens. Drupal Gardens is our free SaaS offer. You can go and sign up, get a free website. We have hundreds of thousands of these free Drupal websites. Unfortunately, these free people don't necessarily ever pay, and we still have to keep a MySQL database around for them. The problem with this is even if Amazon's hardware can handle it, when you toss tens of thousands of databases in a single server, InnoDB makes a single file in the data directory for each database, and the file system just locks up on this. And one of the use cases we're using ParElastic for is actually using their multi-tenant, their scale-out solution, but in a clever way where it maps based upon the tenant ID. We turn a Drupal table that has 100 tables times 1,000 sites onto a single 100-table installation. So MySQL thinks it's any normal Drupal application. Really, it's handling thousands of potential sites. So this really shows how great we can go from having, let's say, 20 MySQL servers running this one application down to a handful of servers. And there's lots of different interesting use cases with ParElastic. That's just one of them. So before ParElastic, we had these servers. After this, we're doing this. We're experimenting both with the storage nodes and the processing nodes and all different capabilities. And the big thing is, even though we are a Drupal company, we don't have the capability to go change all of our client applications. Drupal is an open source project. There's 18,000 different possible Drupal modules out there. Any given site may run 500 different modules, and we can't control the SQL they throw. They can go use Drupal's GUI, enable an 18-way left join, and we have no control over that. We have to be able to toss any normal ANSI SQL out there and support it. And Drupal has a number of issues. Maybe we want to have ParElastic go and broadcast out the session table and the ACL table, and then do its distribution based on the node ID. So there's lots of different flexibility here that Drupal can take advantage of to go achieve this scale in the cloud. And unfortunately, there's not a good scale-out cloud solution. ParElastic is one of these up-and-coming players we're very, very excited about, because it's a very, very hard problem to run MySQL in the cloud. Amazon's not optimized for it, and there's a dearth of good solutions out there.
I think it skipped one, but I'll.
Okay.
No, I know how to. So I did mention this is the performance curve, which you were alluding to. Sorry, I didn't come up with the right sequence, but this is native MySQL. This is not with us. For this, I just had about 2 gig of data, and I just distributed it over a bunch of databases. It could either be all 2 gig in one database, or it could be 2 gig in about 2,000 databases. It's the exact same data set. And you run exactly the same number of queries concurrently at it. That's the response time. Just the fact that you have 2,000 databases and MySQL goes off the cliff. That's the problem which we address.
Yes, it's a tough problem. Yes.
So the multi-tenancy with something like Drupal, I take it behind the scenes, there's an attribute being added to every table to partition people.
Automatically, that's the part we like.
There's 0 lines of code change as far as Drupal is concerned.
Okay.
Behind the scenes, we figure out which tenant a piece of data happens to be, or which tenant a query happens to deal with.
Okay.
And one tenant shall never see another tenant's data.
Okay. And in implementing that, did you run into any weirdness with the optimizer? Like, did some queries need a little more handhold? I assume did it just work out of the box and there were no query issues?
0 lines of change on Drupal's side.
In this case, the underlying MySQL nodes don't know any different, because it's just automatically translating the queries and saying, I want the
But every table now has another attribute.
And in some cases, if there's a table that doesn't have an index, ParElastic can perform better just because it's handling those indexes for that.
But you added an attribute to every table.
They
We
do
had
automatically.
a bunch of data too.
Which meant you put that at the head of every index, probably also that already existed.
And some other things as well.
So that's my question. Did in the implementation itself, were there weirdnesses with MySQL?
So in the implementation, are you talking to Andrew or you're talking to me?
You didn't make any lines of code changes. So
as far as the application is concerned, it created a database. Create database in Callahan. Okay. I sit there and say, yep, create database in Callahan. Create database in Law. Oh, yeah, create database in Law. What we did in the background was we said, oh, there's a new tenant called Tim Callahan. It's fine, you got it. He's got some attributes, his ID or whatever. Create table node. Node is the table which Drupal stores most of its stuff in. Okay, the node table has a little bit of extra payload. Create index IN1 on node, something or the other. Oh, okay. Maybe the create index has a couple of extra columns. Maybe when you create a table, we create a column and an index on those magic columns as well. That's all stuff which the applications knows zip about.
Mm-hmm.
So is there like a master node where you're giving that information, or is it taking the database scheme and implying certain things about it? Like, how is it?
Sorry, ask me your question.
So I think where you're going with that is like there's you have the schema from Drupal. You already know what it is. Mm-hmm. Is there an analysis tool on a master node from ParElastic that's analyzing that and then structuring how to divvy it up?
So a priori, an administrator says, this is my schema set.
Right.
A priori, therefore, if we wanted to distribute data in some way, we would be doing things like that. One of the things which Andrew mentioned was the thing we're distributing on is the magic tenant column. Therefore, there is no analysis of the schema required because a tenant is going to land on a database server. Which database server? That's our problem. Their application doesn't need to know. That's the difference.
We can run 2 different versions of Drupal, actually. We can run Drupal 7 and 8. ParElastic will handle all of that. So when we issue a create table or an alter table, it does automatically in the background. Be able to do this. Maybe 500 databases on the same set of servers is running Drupal 7 and 500 running Drupal 8.
And you can upgrade one of them, and you can customize one of them by adding a new module which creates an extra table. All of that stuff is taken care of. That's what we do. The application, zip.
And then are there other plans from a Drupal perspective for big, like the White House site where they want to be
Yeah,
database farms?
there's a lot of use cases. We're running sites, like I said, big media properties. We're doing probably half a dozen different sites for the Olympics. So there's lots of really spiky traffic where cloud databases make a lot of sense, being able to just add nodes on demand, spin that for a couple hours and spin them down. It's very hard to do this manually with MySQL. You have to implement sharding and rebalancing, all this stuff. And even Amazon RDS doesn't do a lot of these things. They're just pretty basic, master replication. So yes, that's the next use case we're going down. ParElastic is solving the problem we have right now in our SaaS solution, but really, the other hard problem we have is doing the scaling down horizontally or the massive load spikes. Because we have Akamai for the CDN capabilities, but there's really no good solution for the database.
How about, you talk about the application, how about the administration side of it? Is it also, in a sense, virtualized to take advantage of the
We'll see
solution?
some of that. We'll be talking about that during the UI. Two parts to your answer. One, a large portion of the administration, it looks like MySQL. So a class of administrator stuff is exactly identical. There's a bunch of servers, so there's a bunch of administration of a bunch of servers. That's an independent thing. That's done differently.
Oh, I'm thinking about things like having a backup kind of things, and to be able to have certain kind of copy of the data and that kind of.
In our case, MySQL dump still works. We can dump the whole database. We can go do a volume snapshot in Amazon. So all the same backup systems we use will go work with this. It's like a MySQL server, any other MySQL server.
With the multi-tenancy, do you also handle shared data? So if you have a shared common database that may be read-only for your clients, but there's a master that has the right to it, can you handle that?
I don't think we're using it for Acquia, but we do support that. One place where we've talked about it for Acquia is the notion of a common set of users across all sites. Otherwise, I have 10,000 websites, right? You have a website, Tim's got a website. Users on your website are different from users on Tim's site. We give you the ability, if you so desire, to have a common set of users for all sites. This is very useful if there's an intranet style portal where you have 500 portals within your company, but all your users are coming out of a common pool. We do support it.
Apologies if I missed this because I couldn't tell it, but how do you handle fault tolerance, redundancy, failover?
You didn't miss it, we didn't talk about it, but we can talk about it after. I knew I was going to run out of time, so I didn't put any of that in the presentation, but we can surely chat about that.
Okay.
We do handle that.
This sounds like it works if you have a cloud solution for your databases like Amazon. If you have your own iron in a data center.
We're working with somebody who has a lot of iron in their own data center. It works just fine.
So if you add something that requires where ParElastic decides, oh, I need a new node, it needs a new piece.
So the mechanism in which we go and get a new node is eventually it's going on Andrew's credit card. All right. So he's the one who has to decide whether we get a new node or not. We make a call out to some piece of code which Acquia controls and says, yep, we get another node. So eventually there's a check there. That
So
plugin,
you assent to a new node even at Amazon. In other words, it doesn't automatically spin up new nodes for you. You have to actually authorize.
Not yet. We could go do that either with CloudFormation, some other system, but we haven't yet gotten that far.
but in your private data center, so talk about another cloud. We're working in Joints Cloud as well. The mechanism to provision a new node in Amazon is one. The mechanism to provision in Joints Cloud is different. In HP's cloud, it's totally different. We have a mechanism by which the application raises an alert and says, I need a new node. You can automate that portion which goes and provisions the node, brings it into the fold, or you can make it manual.
I have a question about another scenario. For example, I have only one database, and I would like to accelerate it. And I would like to copy that to another server, and now I run under your, but exactly the same copy, and I expect that you will be able to accelerate my queries.
Yeah, the way in which you do that with us is you define all your tables as broadcast, and we'll go round robin and bounce between the servers. Yes, it works. You can define it as broadcast on 6 servers if you want, and we'll just we'll do load balancing across them. If you ever make a write, we're going to make the write to all 6 places. So if you're making a lot of writes, remember, those are transactionally consistent.
Yeah. Anyone wants to talk about Drupal or Opera afterwards, reach out.
So for those who are not on a cloud but are on a private cloud, what's the fingerprint of a node?
A server running MySQL with 2 CPUs and 8 gig of memory. It could be virtualized on whatever hardware you want. So you happen to have a server with 64 gig of memory and 16 cores, and you run VMware or Zen or whatever, and you chop it up into little pieces. Okay, that's a node.
And for the on-demand creation of a node, does it have the capability to access an API, take a template, and create an instance and boot it up, and then?
The way in which we do it in Amazon, which might be an analog for you, is we'll create an AMI which has that. So when I need to spin up a new one, I just say that image, fire up one more. And that image is going to be fired up with some orchestration mechanism where that node is going to come up, it's going to register with something, it's going to get an IP address, and I'm going to say, oh, new compute node. Exact same thing you can do in your own data center. The code for that is not something we would have, but happy to work with you on that. Okay. So multi-tenancy, the challenges you're going to have. We talked about all of this, and PowerPoint is not my friend today, but I think they went out of order. We talked about all of these things. I'm going to skip right over them. This was your question, Tim. The last little piece. For multi-tenant, we can use all of the above distributions, but we can also distribute based on the tenant. Therefore, a tenant goes to one database. Okay. With that, so how many of you have tweeted about us during this demo? The usual suspects. Let's see if I can make this work seamlessly. Looks like you didn't get anything there.
Okay.
You did, cool. All right, so for the purposes of this demo, we're going to demonstrate, we're going to have a couple of windows up here. This is a window onto our management console. I can walk you through a couple of the things we have set up here. I'm going to drop right down to the place where all the fun stuff happens. And on another tab, I'm going to pop open a blog. This blog happens to be Drupal running on top of ParElastic, unmodified Drupal, to your point, Tim. And the data for this Drupal itself is distributed over a collection of 5 sites. So if I go over here, refresh my screen and come on back, you'll notice that all the activity goes over 5 sites, and we happen to be using one dynamic site or one compute site. That's the one here. By the time I walk over, the bar will probably go away. There it is. Okay. And over time, you're going to see more activity. But what we did just to demonstrate what we're doing is we made a blog, and has to do with cloud. So we took a bunch of hashtags which relate to the cloud, and we're just going to use Twitter as a source of data. So you tweet about us, and it should show up on this blog. But, oh, by the way, by virtue of the fact that I just turned on Twitter to ingest data, you notice it's ingesting data into a bunch of databases. So anybody who wants to tweet about us or things like that, your data is going to show up in that database pretty quickly. All we're doing is using Twitter as a data source. Question? You had a question? No? Okay. You're telling me you put a tweet in there, huh?
What hashtag should we use?
Oh, how about found ParElastic?
One, good one too. No shame.
Well, I just turned it on.
Isn't ParElastic on the database?
Oh, the big data block. No? No, not yet. You sure you did? Lawrence?
I did the pound policy.
Oh.
Yeah.
Well, they're not on my screen, so it doesn't count.
Your guy's saying he did.
Yeah, I know.
Yes, you want.
I'll
Okay.
fail well. I'm going on to fail well.
Well, let's turn that off for a while and we'll do. So Ken, to your point, I believe it is. Okay. All right, so no idea why that didn't work out, right? But let's do this since. So I have a bunch of blogs here. I'll pick Bravo. That's the one which happens to be the one with ParElastic and stuff. I have a bunch of queries here just to show you live what happens when you run them. So for those of you who are not familiar with the Drupal schema, everything gets stored in a table called node. All the fun stuff gets stored in a table called node. And the node table itself happens to be distributed over a collection of servers, but the data is distributed based on node ID. So when I run this query, select node ID title where node ID less than 20. Of course, in practice, that query has to go over a bunch of servers. We can get it to run now. Okay. I just lost my internet connection to boot. So rather than making you all sit and wait and watch me figure out why the demo doesn't work, we'll figure out the demo out later. Other questions? Yes?
May I continue my example of multiple exactly the same databases?
Yes.
So I have like 6 of the same database, and you can handle that case. And suddenly, in the middle of the query, one of the node failed. Are you going to deliver the solution to me, or you say, sorry, one node failed, I cannot deliver that?
Depending on the state you're in within a transaction, we may or may not be able to restart your query. But it depends on where you are within the transaction. So let's assume you started an explicit transaction and you made some changes. And then there's an error. The underlying MySQL database, and again, we're not a database. If your underlying MySQL database decides it wants to roll back the transaction, your transaction is rolled back. We don't have much of a choice in this matter.
But in case of just select statement, why I'm asking, because 6 database has exactly the same information as a 1, and just I multiply that, so I'm going to get not only performance increase, what you are doing, but also huge tolerance. You know, fault resistant and all of that stuff, just running your application. And if you cannot deliver me from 5 database, I would be kind of a little bit surprised.
So the answer is, I don't think it's that easy. I'll turn the question around to you this way. Let's assume that I have a MySQL database, one MySQL database, and all the data is replicated and all of that stuff. And I issue a query to it. You're halfway through a query. There's a failure. what do you get? You get an error halfway through the results set. I just now have 5 databases. I broadcast all the data. The data is exactly available in 6 places. I'm halfway through a query. I've returned to you 13 rows. And then there's an error. How do I know where to restart? I don't know whether your query is returning you results in order in a deterministic way or not.
But if the node failed before I started the query, even I had 6.
If the node failed before you started the query, no problem. Absolutely, we'll pick another node, we'll run your query, you'll get your result. The hard case is mid-query restarts. There's a whole bunch of research on how you want to solve that. I don't think there are, good universal style solutions. Yeah, if it's before a node fails, yeah. These are
So if it's mid-query, you return the same error results that you get on a single database?
That's correct.
So as long as from an application perspective, this is-
From an application perspective, you get a partial result set and you get an error. Your application might either retry the query or it might throw up its hands and do whatever the
but
application
if it
does.
does something appropriate without, then it'll do the same thing.
Same kind of thing, exactly.
What do you do if there's a failure with the first reporting results? So the queries is running, there's a failure, but no results have been returned. Do you restart the next scenario?
So long as you're not in an explicit transaction context, we can restart the query and everything will work fine. If you are in an explicit transaction context and before we return results there is an error, then it's dependent on what the state of the transaction below you is. If the transaction was rolled back for you by one of many databases, the net result is your transaction got rolled back by all of them. If no transaction rollback occurred, you're still okay, you could get away with it, you might get your results. Other questions? No? Yes?
At some point you mentioned you're going to talk about costs.
I was going to talk about performance costs. Are you talking about dollars and cents costs?
Either way.
This gentleman would love to tell you about dollars and cents cost. Dollars and cents cost, I'm told, is outside of my pay grade, so I'm not allowed to talk about it. Yeah, they'll beat me if I do that. I'll figure out what's wrong with this demo shortly. Probably too late, though. No, we can't seem to get to it. Okay. So what are we up to? We're based in Waltham. We're also in Toronto. We're hiring, in case you're interested. And we make a group of databases act together as if they're one. The number of databases changes based on size, workload. We're in closed beta, so if you're interested, yeah, absolutely. Happy to chat with you about that. And with that, some contact info as well.
This is for MySQL.
Right now it is. The prototype that I made a while ago works with MySQL, PostgreSQL Server, and Oracle. I couldn't get DB2 for free. Nobody was using it, so I'm using this for. But from a go-to-market perspective, it's MySQL only. Right now works with any flavor of MySQL I've seen around. Yeah, if you have an urgent need for another database, I'm sure that you can twist his arm and we'll do the right thing. Other questions? Cool.